Hello everyone, and welcome to the NEATEC Electronics Series. This video is about latches and flip-flops, so let's get started. Alright everyone, so now let's talk about latches and flip-flops. And specifically right now we're just going to talk about latches, alright? And obviously I wrote the word latches right up here. Now latches and flip-flops are part of sequential circuits. And basically a sequential circuit is a circuit whose output depends not only on the present combination of inputs, but also on the history of the circuit. Alright, so up until now you've been dealing with circuits whose output really depends on the current state of the inputs, but now we're looking at circuits where the output depends not only on the current state of the input but the past inputs as well. Alright, so let's talk about the latch. Okay, the latch has two inputs. Okay, the S, that stands for set. Alright, R, that stands for reset. Okay, it's an SR latch, set, reset. Now when a latch is set, the Q output, alright, I'm going to write it right here, Q is going to be high. Okay, for reset, when a latch is in the reset condition, the Q output is low. Alright, now let's look at these outputs. Here's your set, here's your reset, and here are your outputs. This obviously is Q, and this is Q bar, right? Now Q bar, basically from its name, suggests that whatever Q is, if Q is a 1, Q bar is going to be the complement of it. So it would be 0 and vice versa, right? So if someone asked you what state is this SR latch, you have to basically look at the Q output. And if the Q output is high and reset and Q bar is low, it's in the set state, right? So you would say the latch is set. Obviously if Q is low and Q bar is high, then it's in the reset state. Okay? So let's go over a timing diagram for this. This might help make it a little easier to understand. So here are your two inputs, S right here, R, and we have the two outputs, Q and Q bar. Okay? Now since S does not have a bar over it, we know this is positive logic, right? So when S goes high, okay, now reset doesn't have to change. S went high, reset stayed low. What do you think's going to happen? Let me draw this now in blue for you. Q, you know something, I got to get this so I'm going to make this so it's right up and down here for you, right normal here. So when you set it, Q is going to go high, isn't it? And Q bar was high, that's going to go low. Alright? Now, set comes back down to 0. Okay? So, what do you think is going to happen? Nothing. Alright? when set is 0 and reset is 0, it stays in its current state. Okay, so Q would remain high as it is here. Q bar would remain low as it is here. Okay? Now, I'm sorry for this not being perfectly neat. I'm doing the best I can at trying to draw these things for you. But I think you get the idea, right? Now, let's see what happens next. Suppose, I'm going to change colors now. Suppose set goes high again and goes low like this. What do you, and reset stays the same. What do you think is going to happen to Q and Q bar? Nothing. Because when you set it, Q goes high. If you set it again, Q is already high. So it's not going to change. It's just going to stay high, right? And Q bar obviously would stay low, right? Now, let's continue here. What happens now if your reset goes high? Well, if your reset goes high and your set stays low, there you go, right? What's going to happen here? Well, your Q is going to go back being low again, isn't it? But your Q bar is going to be high. Get it? When you reset it, remember, Q goes low, Q bar goes high. When you set a latch, Q goes high and Q bar goes low. Get it? All right. Now, I want to go through the same exercise. However, I want to use a negative logic, because you're going to run into latches that use negative logic as well. So with S, let's think about this now. At this state, I'm just going to draw a little H here. Both of these are high, okay? Because remember, it's negative logic. It's the same as being low with positive logic, okay? So what are we going to do? We want to have a high pulse. We're going to basically recreate this, right? But with negative logic. So this means we'll start here, go low, and go high. And we're going to keep your R input high, right? So what's going to happen? Well, when you set it, this is low, okay, and this is high. So I'm just doing that to make sure this is clear. So when you set it, Q is going to go high, and Q bar is going to go low. Now look, if I had started, you have to start somewhere, right? You have to be given an initial state. I could have started with Q high and Q bar low. In that case, you would not have seen the transition, because when you set this latch, Q was already high. So that's why I set Q low first, so you could see the transition, okay? Now, we also set it again. So how would you set it again? We're going to drop this set low for a bit and bring it up. There you go. You just set it again there, right? What's going to happen to your Q output? If you said nothing, you're exactly right, because it's already set. You can set it as many times as you want, but the output's not going to change once it's set, right? And how would you reset it? Well, to reset it, you would set your put your reset low, put a negative pulse there. You wouldn't change your set. And what's going to happen when this happens? Well, your Q is going to go low, and your Q bar is going to go high. All right? So the output, if you notice, this output is identical. This output here, the Q and the Q bar, it's the same, right? And we put the same series of pulses in up here, as we did over here. But this side over here used positive logic. In other words, 0, it started at 0 and then the pulses went up, right? It was positive logic. This one, for negative logic, S was high and the pulses were low. All right? So I want to make sure you understand what it means between positive and negative logic, okay? It just defines the direction of your pulse. All right? All right, fantastic. Now look, we're going to talk about the SR latch circuits in a minute, and we're also going to go into truth tables for the latches, all right? And so it makes a little more sense about what we just drew here. Okay, see you soon. All right, everyone. So what I have done is I have kept the circuit with negative logic, okay, over here on the right over here, right? And I drew an empty truth table, okay? And let's go through the exercise here because I want you to understand the truth table for this negative logic latch, all right? So let's start. These are your inputs over here, right? So it's 0, 0, 1, 0, 0, 1, 1, 1, right? We need to know the outputs for each one of these combinations, right? Now remember, these are negative logic, okay? These inputs, right? There's a bar over them. Okay, so in the first case, we have S active because it's low, and we have R active because it's low. Now if you recall, when S is active, we're setting Q high and Q bar low, aren't we? When reset is active, which this is also active, we're setting Q low and Q bar high. This is a conflict, isn't it? So this is called the forbidden state. Okay? You don't want to be in this state. Sometimes it's called the forbidden condition, but you don't want to tell it to do these two things at once because obviously you're telling it two things to do that conflict with one another, right? Q can't be high and low at the same time. Neither can Q bar, right? All right, everyone, so let's go on to the next state. So in this condition, S is active and R is not, right? Because remember, this is negative logic. In this case, we are setting the latch. So that means that Q is going to be 1 and Q bar is going to be 0. Okay? Now, the next condition, well, obviously set is not active, reset is active, so Q is going to be low, Q bar is going to be 1, right? Now, in this in the final condition, 1, 1, neither set nor reset is active, right? So the output does not change. So I call this the no change state. All right? Now, you can go through the same exercise if S and R are not negative logic, right? Obviously, these would just flip, but it's very similar. If the set is active, it's going to set Q high and Q bar low. If reset is active, it's going to set Q bar high and Q low. Now, if neither of them are active, it's not going to change. And if both of them are active at the same time, then you have this forbidden state, and you don't want to go there. All right? All right. So next, I'm going to go over the circuit, one circuit that can be used for the latch. See you in a minute. Hello everyone and welcome back. Now what I have here is a circuit. Alright, one possible circuit for the set reset latch. Alright, if I were to ask you what state is this in, what would you tell me? Look at the outputs here. Q is 0 and Q bar is 1. So this would be in what state? If you said reset, you got that right, because Q bar is 1 and Q is low. So let's go through what happens when you're going to set this latch. Alright? Well, the first thing you would do is this 1 here, right? This would become a 0, right? Now, if 0 comes in on this line, you have an inverter bubble, which changes a 0 to a 1. You have a 1 coming into this OR gate. That means, obviously, with an OR gate, either input, if it's a 1, the output's going to be a 1, right? So that's going to do this. It's going to change this from a 0 to a 1, isn't it? Well, now you have a 1 coming through here. This 1 gets inverted. I'm looking here, if you can't follow my cursor. I'm just coming down this line here. And if you notice, there's an inverter bubble right here, isn't there? That inverter bubble is going to change this 1 to a 0, isn't it? As an input. And you already have a 1 here, which means the output, you have 2 zeros going into this OR gate, which means this 1 is going to change to a 0, isn't it? This 0 is also going to be transferred down here all the way to the input of this OR gate. This is going to be inverted, so it's going to be a 1, and obviously we already have an output of 1 there. It's going to be a 1, get it? So you just went through what happens when you reset. We go from reset to set on a latch. You just set the latch. By the way, this would come back to a 1, right? And when you do that, nothing would change because you have a 1 coming through here on the bottom, get it? So that's it. You just went through what happens when you set a latch. Now, let's go through this. If you're in this condition right here, right? Let's just fix this up a little bit. Let's just get rid of some of the blue. Alright? And we'll make that a 1. Now these conditions right here, we're in set, so Q is going to be 1. Is that right? And if Q is 1, what's Q bar going to be? It's going to be a 0, isn't it? Alright? Now, this latch is in the set condition, right? Just trying to clean up these dashes here for you, so as we don't get confused when we go from set to reset. But it's the same method. Alright, so let's do it right now, okay? And I'm going to change this to, let's change it to a dark green. This will be more fun. So to reset this latch, currently it's set, right? Because Q is high and Q bar is low, right? So if we're going to reset it, we're going to take the reset, we're going to pulse it low because we're going to make it active because there's a bar over this, right? So to make it active, we're going to reset it, we got to drop this low. When this is low, you have an inverter bubble here. This inverter bubble is going to invert that 0 to a 1, and a 1 going into this gate right here, it's an OR gate, you're going to have a 1 coming out, right? Because remember, an OR gate, if either one or both of the inputs is 1, you're going to have a 1 coming out. So that goes to 1, doesn't it? Now, if we follow this back to the input here, the 1 obviously is going to get inverted because of this inverter bubble right here. It's going to make it a 0, right? The other inverter has a 1 coming into it, so you have 2 zeros into this OR gate. That means your output's going to be low. So this is going to be a 0, isn't it? And then your 0 is going to come back here to this gate, where it's going to be inverted to a 1. Alright? And that's going to obviously keep this at 1 because it's already there. And then finally, the reset would go back to a 1, so it's not active. When you do that, obviously this input would be inverted to a 0, but right here. But this input right here is already 0 coming in, and then it's inverted to a 1. So this one's already a 1 coming into the OR gate. So you have a 1 exiting the OR gate. Alright? So if you go through this exercise several times, this may be of assistance to you, okay? It may help you. Now finally, let me clean this up a little bit for you. What's going to happen with both inputs active at the same time? Just getting rid of some of these green marks here. You can fix up your own notes at this time if you would like to. Alright, that's pretty good there. So let's try this, shall we? This is a 1, this is a 1. Let's just have it in the set state, okay, 1, 0. Now suppose this goes to 0 and this goes to 0. Well, what's going to happen? When this goes to 0, you're going to keep your 1 here, aren't you? Got it? Just remember, only one input on an OR gate has to be high for an output to be a 1. Well, if you have an input that's a 0 and it goes through this inverter bubble right here, that means you have a logical 1 or logic high coming into that OR gate, so the output of the OR gate is going to be high, right? The same holds true for reset. If you drop reset or make it active, that inverter bubble right there is going to make it a 1. A 1's going to come out, so this is going to be high. Look, the output of your latch, if you activate both S bar and R bar, your set and reset at the same time, it's going to be 1, 1. Okay? You may have noticed in the prior truth table I actually didn't write down 1, 1. But if we want to do that right now, let's just do it, right? Here's S bar, R bar, it's this Q and Q bar, right? Now, we can simply draw a truth table like this. Why don't you pause the video right now and try to fill it in, and then come back and we'll do it together, okay? Alright everybody, welcome back. So what do we have? 0, 0, 1, 0, 0, 1, 1, 1. That's your inputs, right? So this is going to be 1, 1, isn't it? They're both active at the same time. So Q and Q bar are both going to be 1. Well, this is set, so Q is going to be 1, Q bar is going to be 0. This is reset, it's just the opposite. And when they're both on, this is the no change state. So it's going to keep the value it had. All right? That's important to know. Now, sometimes you're going to see Q and you're going to see a T plus 1 or a T. Okay? That's denoting time, because this value, right, no change. Well, if you want to know the value of it at time t plus 1, that means it's going to take the value at time t. In other words, what it was prior. Remember at the very beginning of this video I said that this kind of circuitry not only depends on the current state of the inputs but also the history? This is exactly what I'm talking about, because if Q and Q bar were in the set state, suppose Q was 1 and Q bar was low, then the output when it's 1, 1 is going to be what it was. There's no change. If it's 0, 1, when it was if it was in the reset state initially and you had no change, well, it's going to be 0, 1, right? So it all depends what the earlier state was. So when you say no change, there's no change from its prior state. That's really what we were talking about there, okay? All right. Let's do one more while we're talking about this. Let's move this out of the way over here. Now what I want to do, let's draw another truth table. Okay? So this one will say S, R, Q, and Q bar. Okay? Notice this is not negative logic I just drew. This is positive logic. I just want to do both for you so to make sure that you get both flavors here. So why don't you pause the video and try to fill out this truth table, then turn it on and we'll do it together. All right, everyone, welcome back. Let's try it. 0, 0, 1, 0, 0, 1, 1, 1. So in this case, 0, 0. Remember, this is positive logic. So neither of these are active, are they? And this, we're talking about this right here, right? This long line. So this would be the no change state, wouldn't it? Because neither set nor reset are active. Here, Q would be 0, and Q bar would be 1, right? Here you're setting it, so it would be 1, 0. Q would be high, Q bar would be low. This right here would be your forbidden condition. That's your forbidden state. Right? All right. Well, fantastic. I think we have pretty much talked about the latch in a very good way. So the next thing we need to talk about is a gated latch. All right? See you soon. All right, everyone, welcome back. Now I would like you to take a look at the circuit in the middle. All right? Right here. Okay? This is the negative logic latch that we've been working with, right? So here is your set input here on top, and there's a bar over it to denote it's a negative logic, right? So low is active. And here's your reset input, same thing, right? Now, I want you to think about this. What I have here is a gate. All right? And what would happen if I took the gate and connected it to the latch just like that, right? Well, first off, look at each one of these gates you have here for the set and for the reset. Those are NAND gates, right? And if you remember your AND gate, right? You have an input, let's just call it A, B, and Y. Alright? And if we want to draw this quickly, you can pause the video and do this. If not, you should be able to do this right now, real time, but let's just try this. This is what? 0, 0, 1, 0, 0, 1, and 1, 1, right? So what's your output going to be? It's going to be 0, 0, 0, and 1, right? For an AND gate. Now, for a NAND gate, let's just continue this over here. If you put an inverter bubble at the end, and this is going to be in the case of a NAND, which is what we have in our circuit, that's going to be 1, 1, 1, 0, right? Because it's just going to be the inversion of the AND gate, right? So, remember our discussion on enabling a gate, right? So if you look at the top one, you have your set right here. If your set is high and you have enabled the gate, which means your enable is high, okay, let's just then suppose, we're looking at these two, suppose your enable is the A input and your set is the B input. Alright? Well, we've enabled the gate, so in this case A is high, right? So what happens now if your set is low? What's your output going to be? Your input is low. For a NAND gate, your output's going to be high, isn't it? And if your set is high, what comes out of that gate is a low. Get it? So really what you've done here is when this is enabled, right, you've basically changed this gate to a positive logic here, right? Notice there's no bar over set and reset. Get it? And now you can control it using this enable, which means you can turn it off. Right? So when I say turn it off, what I'm saying is if these are 0, A is 0 or B is 0, your output is always going to be high, right? Here's a 1 and here's a 1. And if they're high, that means the S bar and the R bar are not going to be active, right? They're going to be in that no change state, so nothing's going to happen, right? No matter what you do to S and R, if the enable is not, if these gates are not enabled, if this enable is not high, nothing's going to change on the output right here on either one of these. All right? Those are sometimes called steering gates. Okay? Now let's look at this even further. I'm going to have to take this space from you, all right? But let's try this now. If you have an enable pulse, let's call it enable, right? And then you have your S and your R inputs, right? What's going to be the outputs? Q and Q bar. Well, let's draw this like we normally do, right? So let me give you a little bit of hint here. Suppose you enable this thing, right? This gate. That means you're going to have four different rows because it's enabled, right? Because remember, your set and reset could be 0, 0, right? 1, 0, 0, 1, and 1, 1, right? And when it's not enabled, Your set could be either 1 or 0, and your reset could be 1 or 0, right? So what would that be? That would be no change, right? Got it? Now, basically it's inhibited. It's not going to change regardless what S and R was from its prior outputs. So if your enable is active, let's look at your set and reset. If your set and reset are low, okay, this is no change, right? Right? Now, in this one, you reset is active, right? So this would be, in this one, set is active. In this one, both are active. This is your forbidden. That's your forbidden state, right? Now when I said this, when I said no change, that's actually correct, but I think how this is most normally stated in literature that you're going to see, instead of saying no change, that usually belongs to this change, the no change state up here for the latch. This would just be not enabled. But if it's not enabled, it's just going to hold its value, whatever it was, so it's not going to change, okay? So that's what this steering gate does, okay? Now, I want you to think about this. Suppose that you pulse that gate. In other words, if you go through time, you just have a little pulse there, ever so often. Think about your circuit, right? That means it's only going to look at the inputs of S and R at the time when your enable pulse is high, right? And that is going to be the only time you would expect to see a change in Q or Q bar. All right? That's pretty ingenious, isn't it? Now, by pulsing that gate, then, you can determine when you want to read those inputs. That's what we're doing here, right? And that means then you can determine when the output would actually change, okay? All right. Now, and next we're going to talk about the transparent latch, all right? And it's going to use some of these, the circuit's going to change slightly, but it's going to use the concepts we just discussed, all right? See you in a minute. All right, everyone. As you can see, I made some slight changes to our circuit. The negative logic SR latch in the center here, right, is still what it always was. I didn't change that one, but our steering gates changed, right? You no longer see an S and an R input, do you? So we connected them both right here, and as you can see, we have an inverter right there. So remember, D stands for data. This D can be a 1 or it can be a 0. That's all, right? Your enable can be a 1 or a 0, and that's all, right? So let's take these and put them together, shall we? We take them and put them together. There you go. So this is sometimes called a gated D latch or a transparent latch. All right, and you'll see why in a minute. So let's just talk about this right now. I'm going to change the color to blue so you can see what I'm discussing. So if we're at this point and we over here and we have a 1 coming in on D, suppose your data pulse is high. Well, that means that your S bar is going to be low, isn't it? So I'm going to write a 0 here. If this is 1, remember, since you have an inverter down here, right? You have an inverter down here. That means your input here is going to be low, isn't it? And if that's 0, that means your output is going to be a 1. So in this condition, you're in set, right? Because remember, S has to be low, and this is S bar, right? Right here we're talking about. So this is set, so you're going to end up with that, right? You just set it, right? So let's just make our truth table over here, shall we? So we have enable, right? And we have D, and we want to know what Q and Q bar are, right? So there's that. There we go. So at this point, enable is equal to 1, right? We're going to do another case. Actually, so we started with D equals 1, didn't we? So let's just do it in order. So when D is equal to 1, we just said Q is equal to 1 and Q bar is equal to 0, right? Now, let's change this, shall we? I'm going to erase the blue marks here. And instead of D being 0, I'm sorry, D being 1, now we're going to make it a 0. So if D is equal to a 0, okay, that's what we have right here, okay, doing the first one. That means this input's going to be 0 right here, right? And if that input is 0 into this NAND gate, okay, you know your output is going to be a 1, right? So it's not activating the set because the set has to be low. On the other hand, since we're going through this inverter down here, okay, D is going to change to a 1. A 1 coming into a NAND gate like this, right? We'll make sure the output is a 0, which means this is in reset, right? Reset is going to be 0, 1. And so we could write the 0, 1. Get it? Now, what happens if your enable is 0? Does it matter what D is? It could be a 0, it could be a 1. Remember, the X stands for I don't care. It could be either 0 or 1. It doesn't really matter. So what's going to come out here, as we talked about earlier, is a no change from what it was previously, right? And sometimes this is, again, not enabled, right? But the reason why they call it a transparent D latch is, look, if your data coming in is low, Q is low. If your data coming in is high, Q is high. So it just lets your data pass. It's transparent when it's enabled, right? If you needed to use the inverse of it, obviously you have Q bar available to you. But that's basically what it is. So you can turn it off. If you don't enable it, then your data is not going to go anywhere, right? All right. I think you understand latches quite well. Now we're going to make the jump from latches to flip-flops, okay? See you soon. Alright everyone, welcome back. So now let's talk about the flip-flop, okay? There are quite a few different types of flip-flops, alright? I'm going to discuss two of them. One is the D flip-flop, it stands for data, and the other one is the JK flip-flop. You know, I don't know what J and K stand for. I don't think there are words that those things stand for, but the JK flip-flop and the D flip-flop are pretty standard flip-flops. And if you know how these flip-flops work, I'm sure you can figure out other flip-flops, okay? So the generic flip-flop I've drawn over here, okay, on this side, and as you can see, they all have a clock input, right? And they have two outputs, a Q and a Q bar, all right? So, since we're starting with the D, I'm going to draw the letter D up here. D stands for data, and there's your input, all right? So first off, I want to make sure that you understand that basically a flip-flop is a latch whose output changes when the clock receives an edge, right? So we're talking about this input right here. So if you have a clock pulse and it does this, that's your rising edge, or there's your falling edge, right? It depends on your flip-flop, but it has to receive, it's going to clock either on the rising edge or on the falling edge. So just be aware of this. If you're in the lab, you're going to most likely connect your circuit to an oscilloscope so you can actually see when the transition occurs, all right? Now, in the data sheet for the specific flip-flop you're using, it's going to state if it's a positive edge triggered or negative edge triggered, all right? So I just want to make sure that we all understand that. Okay, let's get back to the flip-flop here, shall we? So, if you have a 1 coming in here, let me write this down. 1 coming in here, and then you clock it, okay? And I'm going to just use this as an example, pretending it's a positive edge clocking, okay? Could be negative edge, we don't know that, but we have to assume something, so we're going to say a positive edge. That means it's going to clock the data pulse on through to Q. Get it? Q follows D. Remember that, okay? On the other hand, if your input is a 0, and then you clock it, then your output, Q, is going to be a 0, and Q bar is going to be a 1. Now, did you listen to the order in which I said it? I said if you change Q or D to 0, and then you clock it, then your output's going to change. Q will be, well, whatever D is, right? If you don't clock it, Q is not going to change. Got it? So that's very important to understand that. So let's just draw a truth table here, shall we? There's your clock pulse. That's your D, that's your input. And then we'll talk about your output. Q and Q bar, okay? Now generally how it's denoted is this will be T plus 1. T stands for time. So this is after it's clocked, okay? So if I'm drawing this right, come right like this. Montgomery like this, down like this, all right? So let's go back. Suppose we have a positive edge triggered like we said. Now we're going to denote that by an arrow pointing up. Sometimes you're going to see on a data sheet that, okay? That's going to denote an edge, okay? Just be aware of that, all right? So let me take that off. So on a positive going pulse, if D is 0, what's Q going to be after it's clocked? We just said Q would be 0 and Q bar would be a 1, right? So if we change D to a 1 and then we clock it, what's Q going to be? Q is going to be a 1, Q bar is going to be a 0, right? Obviously this is going to be set and this will be reset. All right? Now, if you don't have an edge, it doesn't matter what D is, because this is going to stay what it was. And instead of T plus 1, it's just going to stay at QT, and this will be Q bar T. Now look, there's no change in the output. Okay, that's what they're saying here with T, because this is at T plus 1 for this one and this one. It's a T plus 1, T plus 1. T plus 1 means after it's clocked. Now, since we don't have an arrow here, it's not an edge. It was never clocked. If it's never clocked, it's not going to change. So they denote that in some truth tables as Q sub T. Okay, you might even see no change. All right. Now, guess what? Suppose it's a 1. Doesn't matter what X is. It's the same thing. Q sub T, Q bar sub T. And guess what? If it's a negative going edge, it doesn't matter what D is, it's going to stay at Q sub T, Q bar sub T. Got it? So you have to, the clock has to have a positive going edge for it to clock D through. Got it? On this specific flip-flop that we just talked about. Now, let's talk about the JK flip-flop, all right? Remember, for the D flip-flop, Q follows D, all right? But now we're going to talk about the JK flip-flop. Let's just see what happens here. Get rid of this one. All right. So we're going to have two inputs now, right? J and K. Okay? Now, why don't we actually write another truth table, shall we? This one we're going to have a clock, J, K, those are your inputs, right? Then we're going to have Q, T plus 1, Q bar T plus 1. All right, this is useful for you because when you're looking at different data sheets, they're going to use T plus 1 and T, so it's a good idea. And they could use it on, I mean, they could use it on other chips as well, right? So you understand this, it helps you for a variety of gates and things. Okay. So, we talked about this. We have a positive going pulse, right? That's just an arrow. Now, suppose they're both 0, all right? Your output would simply be what it was. There's no change, okay? That's when they're both 0 when it's clocked, okay? Now, again, suppose we have a positive going clock pulse, and now we're at what? 1, 0. Standard truth table, right? You notice we started 0. 0, 0 is binary for decimal 0. 1, 0 is binary for 1, right? And then we're going to go 2, and you'll see. So this one right here, K is 1 and J is 0, right? Well, if K is 1 and J is 0, this is going to come out as Q bar is 1. Q is going to be 0. And this will be in reset, won't it? Got it? How about this one? What do you think that's going to be? 1, 0. That's going to be set. Got it? What happens there, and you get a pulse. Okay. This is going to be called toggle. Now, how that's going to be represented is that's going to be Q bar T and QT. Get it? So, quite simply, if you were in the set state and then you both J and K were high and you clocked it, it would go to the reset state. And then if J and K were still high and you clocked it again, it would go to the set state. It would toggle back and forth. That's why it's called the toggle. All right? Now, for everything else, if this was a 0 or a 1 or it was a negative going pulse, it doesn't matter what these are. Okay? So these pretty much are going to stay Q, T, Q bar, T. Okay? So all of these, they don't change because it's looking for a positive edge, right? Positive edge to clock it, and then when it doesn't get it, it's not going to do anything, so it just stays where it is, right? That's pretty much no change. You might see this as inhibited, but it's really also no change, okay? Let me just call it NC. So it's not going to change if it doesn't see an edge, a positive edge on your clock pulse, okay? So that's your edge triggered flip-flop right there. Your D and your JK, all right? All right, everyone. Fantastic. We got through the latches and we got through the flip-flops. Fantastic. I believe in the future we're going to use, we're going to talk about counters, and counters are going to make use of these flip-flops. All right? It'll be exciting to see it put together. All right, folks. See you soon.